Alright, let's get started with Lesson 1, Part 2 on electromagnetic waves. Remember, an electromagnetic wave is just light that's radiating out from a charged particle that is vibrating. And electromagnetic waves are made up of an electrical wave and a magnetic wave that are traveling together, that are perpendicular to each other. Alright, so what we're going to do is, now that we understand what an electrical magnetic wave is we're going to talk about what is known as the electrical magnetic spectrum. So different types of electrical magnetic radiation exist. They differ only by their wavelengths and frequencies. The types of electrical magnetic waves range from very large wavelengths, which would be radio waves, that are emitted by antennas, to small wavelengths associated with what are known as gamma rays, which result from charges in the nucleus of atoms. The range of electromagnetic waves make up what is known as the continuous electromagnetic spectrum. The spectrum is continuous because each type of wave merges into the next without a break, and you should become very familiar with the electrical magnetic spectrum. Alright, before we get into the overall spectrum idea, what we have is a prism. A prism is a special piece of matter that when we pass light through it, or electrical magnetic waves, it causes them to break apart into component different wavelengths and frequencies, like we see here. So this prism, we are passing white light through it, and then the prism bends that light. As you can see, it's bending it, and when it bends that light through the prism, it breaks the white light down into different colors of light, and each one of those colors has a different wavelength and a different frequency. Alright, so each of these individual colors that you see right here are electrical magnetic waves, and the difference between them is their wavelengths and frequencies, which then generate the different colors that we see. So when we see white light, and any time that passes through a prism, the light waves are bent, resulting in that continuous spectrum of colors that we saw on the previous slide, and we also see right here. We can see white light passing through, the bent, separating in the different colors, and we get a continuous spectrum. And that's important to understand. A continuous spectrum, meaning that they blend together, all the wavelengths, all the frequencies blend together, or these colors blend together. Alright? Generating electrical magnetic waves that are red, orange, yellow, green, blue, indigo, and violet. Okay? These are the colors of the rainbow, which you should know as Roy, G, Biv. Red, orange, yellow, green, blue, indigo, and violet. And so this is a continuous spectrum of visible colored light that we have the capability of seeing. Now the difference again between all of these colors is the wavelength and frequencies that the electromagnetic waves have. Right? You can also see this with a DVD or a CD. If you shine some light on it, the white light will bend and break into a color spectrum, or a continuous color spectrum that we see here. Alright, this is one of the most important charts in this lecture video, and that is, this shows the overall continuous electrical magnetic spectrum of all light. Okay, so we're gonna label some things here in this electrical magnetic spectrum. Over here, where we have radio waves, this is large wave lengths. Okay, large wavelengths. That looks terrible, but you can think these are the large wavelengths over here, and over on the other side, where the gamma is the small wavelengths. So we have large and small. All right. So as we move from radio waves, we move to television, to radar and FM radio waves, microwaves, infrared, and then right in the middle of the electromagnetic spectrum of light is the visible spectrum, which we'll come back to, and then we have ultraviolet light. Ultraviolet light is what causes us to get sunburns or for us to tan. X-rays, which we know we can use for medical purposes, and then gamma rays, which are generated by the nucleuses of atoms. All right. So the wavelength then is going to get smaller as we move towards gamma, or in other words, it gets bigger in this direction here. All right. All right, let's talk about the visible spectrum of light really quick. Remember, the visible spectrum is right in the middle. It has wavelengths of 700 nanometers. Wavelengths are in nanometers, so 700 nanometers to 400 nanometers. Red has the largest wavelengths, and violet has the smallest wavelengths. I will expect you to understand and know that. All right, so you need to know Roy G. Biv, the colors of light that we can visibly see. Has a wavelength range from 700 to 400 nanometers. You need to know that wavelength range of the visible spectrum. Okay. Now, for the other wavelengths of the electromagnetic spectrum, from radio to gamma, I don't expect you to know those wavelengths just for the visible light. I just expect you to know that radio waves are at the largest, or the largest wavelengths, and the gamma are the smallest wavelengths in the electromagnetic spectrum. Now, all the other forms of electromagnetic spectrum, from radio to infrared, we cannot see with our eyes. We don't have the capability. Our brain cannot see those wavelengths and interpret them as any particular color. The same thing with ultraviolet, X-ray, and gamma rays. Our eyes are incapable of deciphering color from those wavelengths. Now, other organisms might be able to do that. We cannot. All right? We can't detect them. Our brains are unable to do that. So all we can do with our brain is detect the visible spectrum, and this is where we see color in our lives, is from wavelengths from 700 to 400 nanometers. All right? So that's important to understand. Again, all of these are forms of light. Everything that we see in the continuous spectrum. That's right. Even radio waves are forms of light. Gamma, X-ray, ultraviolet, infrared, microwaves are all forms of light, and the only difference between these forms is the wavelengths and frequencies which they have. All right? Now, we just said that wavelength is increasing as we move away from gamma to radio. The frequency is going to be just the opposite. It's going to get bigger as we move from radio to gamma rays. The frequency gets bigger and bigger. And so when we look at the visible spectrum, for instance, the frequency should be getting bigger as we go from red to violet. So violet light should have the highest frequency, but the lowest or the smallest wavelength. And red light should have the smallest frequency, but the largest wavelength. So basically, we would say that wavelength and frequency are inversely proportional to each other. Now, what about the energy that these light waves or electromagnetic waves have? Well, it turns out that the energy that these waves have is proportional to the frequency. So in other words, as the as the frequency begins to get bigger, so does the amount of energy. Or in other words, as the wavelength gets larger, the amount of energy that a wave has gets smaller. All right? So frequency and wavelength goes the same way. It goes the same way, or frequency and energy goes in the same direction, and wavelength is inversely proportional to both of those. We're going to spend a lot more time on that a little bit later in lesson number 2. But what I want you to walk away with is that violet light then has the most amount of energy, and red light has the least amount of energy when it comes to the visible spectrum. All right, so let's summarize really quickly. Red light has the smallest wavelengths, red light has the largest wavelengths, the smallest frequency, and the smallest amount of energy in the visible region. Violet light has the smallest wavelengths, the largest frequencies, and the largest amount of energy in the visible region. All right, so overall then, gamma rays would have the greatest amount of energy. Radio would have the least amount of energy on our electromagnetic spectrum. Okay? Hopefully that makes sense. All right? All right. Finally, we're going to finish up. We've already kind of mentioned this, but let's do this formally and officially. The relationship between wavelength and frequency. The wavelength is inversely proportional to frequency. Now, we can place an equation for this. So the equation that we're going to use is C. Now, C is going to stand for the speed of light. And you learned this in the last lecture video, that the speed of light is 8.00 times 10 to the 8th meters per second, and it's constant. So the speed of light is equal to the wavelength times the frequency of light. And so what this shows us then, as if the wavelength goes up, the frequency must go down. And so therefore, they're an inversely proportional relationship. Now, I want you to know this equation. Know it for the quiz. You're going to be doing some homework problems using this equation. And it will also be on the test. So walk away with it. Okay, I'm going to rewrite this one more time. So the speed of light is equal to the wavelength times the frequency of the wave. Okay? And this is true for all electromagnetic waves, or in other words, for all forms of light. And again, light has the same speed. They just have different wavelengths and frequencies, and this is how they're related. All right, so that is it for this lecture video.